Okay, thank you. Okay, so thank you for the invitation. As I already said, it's my pleasure to have a chance to take part in this very interesting meeting. And so last time we focused on relatively simple and elementary possibilities to stabilize multidimensional solitons, namely using the straightforward competition between the cubic self-focusing and quintic self-defocusing. So obviously the quintic term, being a high ordinal linear term, immediately arrests the collapse, and therefore it opens the way to stabilization of multidimensional solitons. Now, a new direction, which was developed more recently, but it's thus far remains purely theoretical, it makes use of the effect, it aims to stabilize 2- and 3-dimensional solitons and Bose-Einstein condensates, so matter wave solitons, by means of the specific effect, which is called spin-orbit coupling. Okay, so generally, there are many works which aim to use Bose-Einstein condensates for emulation of various complex effects which have been known for a very long time in condensed matter physics. And in many cases, in Bose-Einstein condensates, it's possible to emulate or somehow reproduce similar effect in a much more simple and a much clearer form. In particular, one such effect is called the spin-orbit coupling. So spin-orbit coupling by itself is a fundamentally important phenomenon in semiconductor physics. And the meaning of it is that when the electron is moving in the semiconductor material in the electrostatic field of the ionic lattice, it's actually moving with non-relativistic velocity. There are nevertheless some weakly relativistic effects. So what one can do, one can follow the motion of the electron in the reference frame, which moves at the same speed. And then one should apply the Lorentz transform to the original electrostatic field created by the ionic lattice and transform it into the electromagnetic field in the moving reference frame. So according to the Lorentz transform, for the electromagnetic field, the electrostatic field will generate some small component of the magnetic field. And then in turn, in that moving reference frame, this weak magnetic field will couple to the intrinsic magnetic moment of the electron, to the Boris magneton, roughly speaking. As a result of this, there will be the effective interaction between the motion of the electron and its spin state. This is what is called spin-orbit coupling in semiconductors. Now, in BEC, of course, first of all, the particles are not fermions, unlike electrons, they are bosons. And second, in the real experiments, they don't have any true, at least in the simplest experiments, they don't have any true spin, but it's possible to emulate essentially the same phenomenon by choosing the particular binary condensate. So a 2-component condensate, which is formed as a mixture of 2 different hyper fine states of the same atom, essentially. And then one can apply a specifically designed laser illumination field to this binary condensate. And after some analysis, one can demonstrate that, although physically speaking, it's a completely different situation from anything like the spin-orbit coupling in semiconductors, nevertheless, the effective Hamiltonian in this system will be essentially the same as the fundamental Hamiltonian, which accounts for the spin-orbit coupling in the semiconductor physics. In particular, the Hamiltonian in semiconductors, of course, includes the spinor wave function of the fermionic spinor wave function of the electrons, while in the case of the 2-component bosonic gas, it is a pseudo spinner. A pseudo spinner is simply has two components which correspond to two different components of this binary atomic gas, and they emulate the two components of the spinor wave function of the electrons. So, as I said already, it's possible to demonstrate that one can design an optical illumination of this condensate so that the Hamiltonian, due to the interaction of this optical field with atoms, will be essentially the same as the Hamiltonian, which accounts for the spin-orbit interaction in actual semiconductors. Okay. So this is a standard model. It's written currently in 2 dimensions for the emulation of the spin-orbit coupling in Bose-Einstein condensate. So phi plus and phi minus, these are wave functions. I guess this cursor is not seen on the white. Okay, so on the white background, so I can use maybe some.
There was the laser pointer.
Where is the laser pointer? Ah, here, yes. So yeah, I forgot, sorry. Okay, yes, okay, thank you. Yes, okay, so these are two components of the wave function. Then these are usual cubic terms which account for the effect of collisions in the mean field approximation. And here the sign minus, which is fixed in front of these terms, implies that this collision is actually switched from the natural repulsive into attractive. I maybe mentioned the last time that there is a fundamental and easy to use effect, which is called Feshbach resonance, which means essentially the application simply of the DC spatially uniform magnetic field, which essentially affects the character of the collisions between atoms and eventually makes it possible to control both the magnitude and the sign of the effective cubic nonlinearity. So the natural sign would correspond to repulsion, but it's known that in many species such as lithium-7 or rubidium-85 or potassium-39, it's possible to switch it into attraction. And now, so we have self-attraction in each component, and now these terms, which are linear, they exactly represent the spin-orbit coupling. So the spin-orbit coupling by itself is a purely linear effect, because it's represented by the linear combination of terms. And roughly speaking, what it does, it actually gives rise to the linear mixing between the two components. However, it's not the direct mixing, it's mixing through their first derivatives. Okay, and so the analysis of this system was developed in some work. The very first one we did with my collaborator Hidetsugu Sakaguchi and his former PhD student Ben Lee. The result of this analysis has demonstrated that one can predict new types of two-dimensional solitons in this system, and very surprisingly, they become completely stable. So let me remind that the fundamental difficulty is that if you simply take the two-dimensional nonlinear Schrödinger equation with this cubic self-attraction, as we take here, formally speaking, we do have families of solitons, the so-called tau solitons, but they are completely unstable because of the possibility of the critical collapse. Now we can actually solve this problem. So first of all, the analysis demonstrates that if we look for stationary solutions to our system, one particular type of the solution can be exactly represented by this ansatz. So what is exactly compatible with a specific linear mixing between the two components is the following structure. In one component, we can assume that we have just the uniform wave function. Uniform, I mean, it's only a function of the radial coordinate. It's written in terms of the polar coordinates, radial and angular coordinates. So in one component, it's simply the radial wave function with zero vorticity, with no vorticity. In the second component, it must automatically have vorticity +1. Exactly these combinations of two vorticities, 0 and 1, is compatible is compatible with this structure. Maybe I should jump back. So exactly this combination of the vorticity 0 in one component and 1 in the other, exactly this combination is compatible with this form of the linear mixing between the two components through their first spatial derivative. This is a rather simple mathematical fact. Okay, then this way one can easily solve numerically the remaining equations for this radial wave function f plus and f minus. And the solution with any negative value of the chemical potential mu will be exponentially localized, as the soliton should be. And then one can this way one can produce a family of solitons. So these solitons are called semi-vortices. Semi-vortex. Why semi-vortex? The reason is quite obvious, because in one component it has 0 vorticity, in the other component it has vorticity 1. Okay, so this is a typical example, the cross-section of this radial wave function. So this larger wave function with the maximum at the center represents the 0 vorticity component, and the dashed line with which vanishes at the center naturally represents the vertical component. Of course, if we have the vertical component, it must have 0 at the central point, which we observe here. So they're well localized, and so this is an example of such a semi-vortex soliton, and they can be, this family of semi-vortex solitons can be naturally characterized by the total norm, of course. Now, this simple diagram actually represents the most important result. So what it shows, as it's commonly adopted, if you want to characterize a family of solitons, we can show it by means of the chemical potential versus the total norm n. In the case, if we don't have spin-orbit coupling, we have just a traditional two-dimensional nonlinear Schrodinger equation. Let me remind, we would have simply the town solitons, which are degenerate, so they all would have a single value of the norm. Actually, if here mu runs to minus infinity, the asymptotic value of the norm will be exactly equal to this town's norm. So it means that in the limit when mu is minus infinity, the vertical component will become empty, and the 0 vorticity component will degenerate into this town soliton. However, at any finite negative value of mu, we have both components present here. And then what is very important result is that the norm of each of these solitons is smaller than the limit value, which would correspond to the down soliton. And what it immediately implies, because the norm is smaller than the limit value is exactly the critical norm, which is necessary for the initiation of the collapse. Because now all solitons have their norm smaller than this critical value. None of them is able to initiate spontaneously the onset of the collapse. It does not have enough norm. And therefore, each guy which belongs to this family has actually no other option but to be stable, because this destabilizing factor, the critical collapse, is simply impossible, and therefore nothing else will destabilize the soliton. So the result, which can be checked directly, is that this entire family is completely stable. And by the way, the fact that its slope is negative, the derivative dmu with respect to dn is negative, it also helps to believe that they're a stable family. Why? Because there is a famous not sufficient but necessary stability condition, which is called Vahitov-Kolokov stability condition. So people with this name discovered it very long ago in the former Soviet Union. And their result was that if we have a family of solitons in any dimension, with any nonlinearity, simply supported by some effective self-attraction, otherwise it may be any model, in that case, not sufficient but a necessary stability condition for the solitons is exactly that the derivative of mu with respect to n must be negative. Yes.
In this graph, out of m equals 0,
yes,
mu takes the minus 0.5.
yes, you can very easily analytically demonstrate that this is actually the linear limit when n is going to vanish.
I'm just wondering why mu should take the non-zero value.
Because because we have the additional linear terms in spin orbit coupling, so they introduce a change in the linear spectrum. They shift the edge point of the semi-infinite spectrum band gap. Okay, so then actually, in addition, so these semi-vortices may be called fundamental solitons. One can also construct higher order solitons, so to say, excited states. So the answer is written here. This answer again is exactly compatible with the spin orbit coupling equations. Namely, now what we can do, we can add exactly the same integer vorticity S to both components. So such higher order families also exist, but they are not very important for a simple reason, because unlike the fundamental spin orbit coupled semi-vortex, all these high order states are completely unstable. So this is an example of the stationary solution for the next order excited state. Is the cross sections of two components, the top view, but unlike their fundamental counterpart, they're completely unstable, therefore not very important. Okay, now there is another possibility. We can also, let us look again at the system of coupled Gross-Petaevsky equations with exactly the same spin orbit coupling as before, but now we can introduce this additional nonlinearity with coefficient gamma, which has a very simple meaning. When atoms collide, also atoms which belong to two different components collide between themselves. Previously, in the previous model, we simply ignored this term. Now we can take it into regard, and then we will have the additional coefficient of the nonlinear cross interaction with some positive gamma. And then we can analyze the effect of gamma on the semi-vortices, and the result will be that as long as gamma is smaller than 1, we have essentially the same type of the semi-vortex, and they remain completely stable. However, when gamma is larger than 1, which means the cross-attraction is stronger than self-attraction in each component, we still have, formally speaking, the solutions, but they're unstable. However, when we lose their stability, we get a compensation, because now we may construct an additional family of solutions which are different from semi-vortices. And unlike semi-vortices were introduced by means of some exact answers. Let me remind, one component exactly has vorticity 0, is the companion has exactly vorticity 1, and they're exactly compatible with the spin orbit coupling equations. A new family is introduced by means of this answer, so it's called mixed mode. Why mixed mode? We assume that in each component we have the mixture of the 0 vorticity term and a term which carries vorticity. In one component, in the simplest approximation, -1, in the second component, +1. It's not the exact answer, it's not exactly compatible with the equations, but it's actually a sufficiently good initial condition to numerically construct a Soliton solution of this type, which we call the mixed mode solution. This is a typical structure of the solution shown by means of the cross sections of the two components, continuous and dashed. Now, a characteristic feature is the maximum points of maxima are always split, somehow separated. And then the stability analysis of these mixed mode solutions demonstrates the following result. Let us look again at the coupled nonlinear equations. As long as this coefficient of the cross interaction gamma remains smaller than 1, and as I mentioned in that case, semi-vortices are stable, this mixed mode solitons exist, but they are unstable, not so interesting. However, when we switch to gamma larger than 1, we exactly switch the stability. Namely, the semi-vortices become unstable, but simultaneously mixed modes become stable. So we always have some stable solitons, and actually they play the role of the ground state. In the pure nonlinear Schrodinger equation with the collapse, the ground state actually does not exist. So formally speaking, it corresponds to the collapsing state, which develops the singularity. Okay, so for now it's possible to explain this finding, why the switch of stability happens exactly between the two types of solitons, semi-vortices and mixed modes, happens exactly when gamma is equal to 1. When exactly at the point, it corresponds to the so-called Monakov's nonlinearity. Monakov was a Russian mathematician who was first to study the nonlinear Schrodinger equation in one dimension with equal strengths of the self-attraction and cross-attraction. Okay, so why exactly is the Manakov's case gamma equal to 1? We have the switch of the stability between two soliton families. To understand this, what we can do, we can write the Hamiltonian energy of the system. It's written here in terms of the two wave functions. And then what we can do, we can fix the total norm. And for the total norm, we can plot the energy of Hamiltonian as a function of this critical parameter gamma, the relative strength of the cross-attraction with respect to the self-attraction. So what we see when gamma is smaller than 1, the continuous curve, it represents the energy of the mixed mode. It represents the minimum of energy, therefore it is ground state. Simultaneously, this dashed curve represents the energy of the mixed mode, which is now the excited state. It has larger energy, and therefore actually it's unstable. At gamma equal to 1, the energies become exactly stable. The situation is exactly at gamma equal to 1, more complex. There are some additional stable solutions, but only in this case. And then when we take gamma larger than 1, we have the switch. So now the minimum of energy is provided by the family of mixed modes, and they are now stable ground states, while the semi-vortices continue to exist as formal solutions. Now they are clearly excited states and they're unstable. By the way, this top curve shows that what I mentioned is simply that excited state when we from the very beginning added some equal vorticity to both components. So their energy is much higher, and this easily explains why they are always unstable. Okay. Then another question about the solitons. What about their mobility? If we have the usual nonlinear Schrodinger equation, we have the obvious property of the Galilean invariance, which means that if we have a quiescent soliton with 0 velocity, we can immediately construct a moving soliton with an arbitrary velocity. When we have the spin-orbit coupling, the spin-orbit coupling terms obviously break the Galilean invariance. So this property is no longer valid. And then there is a question if we can nevertheless have moving solitons. This question may be addressed if we simply rewrite our original equations in the moving reference frame. In the moving reference frame, we obtain these additional convective terms. And then in this moving reference frame, it's possible to analyze stationary solutions, which in the laboratory reference frame, which represent, of course, moving solitons. And then we can ask the question, what happens? And the result is non-trivial. Namely, the result is that as we fix all other parameters, for example, the total norm, and we increase the v sub y, and this is the velocity in the y direction, for example. We increase the velocity, the amplitude of this actually of mixed mode. This is a mixed mode soliton. It's top view of the moving components of this mixed mode. Now it's deformed because of the motion. And then what is essential, the amplitude gradually decreases with the increase of the velocity, and there is a critical value of the velocity at which this amplitude becomes equal to 0, which means delocalization of the soliton. So soliton cannot exist anymore with the velocity exceeding this critical value. A similar effect is observed for the semi-vortices, but for semi-vortices, this critical velocity is extremely small. So practically speaking, they are immobile objects. They cannot be set in motion. Mixed modes are more robust objects. One can push them, one can apply kick, and they will agree to move up to some critical velocity. Okay, now, the question is, can these ideas be used to stabilize 3 dimensions? So all this was we discussed this in 2 dimensions. Can similar ideas be generalized to stabilize 3-dimensional solitons by means of the spin-orbit coupling? The answer is we cannot create ground state solitons. Why? Because in the spin-orbit coupling is not able to suppress the supercritical collapse in the 3-dimensional case. However, what we can do, we can predict metastable solitons, which are not ground states, but at least they're stable against small perturbations. Okay, so how this can be done? One can take the 3-dimensional system of coupled equations. This is once again, so this sigma is simply the vector. So this is now this is a matrix form of the two-component system, and sigma is the vector of the three Pauli matrices. So this is just a scalar product of this vector with the null operator. So these are again linear terms which mix two components through their first derivatives. It's not exactly the same as the so-called Rashba spin orbit coupling, which we discussed previously. It's a so-called Weil type of the spin orbit coupling, but it's rather similar. It's not qualitatively different. And then we have exactly the same nonlinearity. So the only difference is that here the relative coefficient of the self-attraction is called not gamma, but eta. Okay. And in this case, one can first of all try to predict something qualitatively. Namely, one can again write different terms in the energy of this three-dimensional system, and then apply the simple idea. The idea is, let us assume that we fix the total norm of this object, and let us assume that we consider this localized state with various values of this spatial size, capital L. Then we estimate, so for the fixed norm, we estimate the scaling of different terms in the Hamiltonian as we vary the size, and then we see that some as L is what does it mean to prevent the collapse? Collapse means that when L is going to 0, the dominant term starts to approach minus infinity. And it means that it is driving the system towards the collapse. Now we can compare different terms in this as a function of L and try to see if sometimes we can suppress this effect of the self-attracted nonlinearity, which is driving system towards the collapse. So this crude analysis qualitatively produces the following crude result. It's it's shown here. So when we have no spin orbit coupling, we have this, and this is energy versus the size L. We do have no minimum of energy. We have only the maximum. Maximum simply corresponds to the very strongly unstable usual three-dimensional soliton, which of course is produced by the nonlinear Schrodinger equation in 3 dimensions, but it is terribly unstable against the supercritical collapse. If the spin orbit coupling is too strong, this green line, then it has no extremum at all. But in the appropriate interval of values, when the spin orbit coupling is moderately strong, what we can predict the shallow minimum of the energy, and it implies that we still cannot prevent the collapse. Collapse means that this blue line will eventually fall towards minus infinity. However, around this minimum, we can have at least a soliton, which may be stable against small perturbations. Indeed, this qualitative prediction can be confirmed by the full numerical solution, as these are examples of solitons which are stable, three-dimensional solitons, which are stable against small perturbations. So they are shown by means of the level densities of the plots of the densities. So this, again, we have two types of solitons. In the top row, we have an example of the semi-vortex. This component has 0 vorticity. This one, it's not very well visible, but you can see some axis. This axis represents actually the vorticity. So this is a vertical component, and this, on the other hand, in the bottom part, these fancy shapes, they represent the stable against small perturbations, of course, a stable soliton of the mixed mode type. It has such a fancy shape just because it's a mixed mode, which mixes different terms with different vorticities and also with 0 vorticity. Okay, now, another possibility to stabilize multidimensional solitons, again, essentially in the two-component Bose-Einstein condensate, but now the mechanism of stabilization is completely different, has nothing in common with spin orbit coupling, and makes use of a completely different physical effect. So this physical effect was theoretically predicted very long ago in 1957 in this classical paper by 3 theoretical people, Li, Huang, Yang. Actually, Li and Yang are very famous people who received the Nobel Prize for the prediction of the parity non-conservation and weak interactions. Both of them are alive now. In particular, Professor Yang is actually not 101, he's now 101 years old. So what they did, they considered the traditional theory of mean field approximation for the gas of bosons, which was originally developed by the Russian physicist Bogolyubov, and then calculated analytically effective corrections to the energy of the mean field interaction, which are induced by quantum fluctuations, because the mean field approximation is a semi-classical approximation. And they picked up an idea, why not to calculate the correction to the mean field produced by quantum fluctuation. So this did it long ago, and much later, there appeared a theoretical paper of a Russian physicist who is a professor in Paris, Dmitry Petrov. And Petrov actually applied, he essentially wrote the Gross-Pitayevsky equations, which explicitly included the corrections of Li Huang and Yang, because Li Huang and Yang, they derived this in their classical work, they derived this for the spatially uniform bosonic gas. The idea of Petrov was why not to apply the same corrections to the spatially inhomogeneous wave functions, which are governed by the Gross-Pitayevsky equation in the mean field approximation. Now we will have the Gross-Pitayevsky equations, but with additional terms. Okay, so what Petrov derived in 2015, it was essentially this equation. So as a matter of fact, it's necessary to consider a two-component gas. Why two-component gas? Because we want to construct something like a soliton. If you want to construct something like a soliton, we must have some attraction. However, this correction of Li Huang and Yang was derived and is valid only for the gas with the repulsive interactions between atoms. Now, the trick proposed by Petrov is, let us take a two-component gas, and each component is self-repulsive, and therefore it includes automatically, if we want to take it into regard, the Li Huang-Yang correction. However, by means of this Feshbach resonance, which I mentioned, experimentally it's quite possible to switch the interaction between the two components into attraction. And then one can consider the symmetric configuration when the wave functions psi of both components are equal to each other. So it's enough to write a single Gross-Pitayevsky equation, not a system of two. And then this effective cubic nonlinearity will be a result of the competition of two terms: intrinsic self-repulsion and cross-attraction between the two components. And then the idea is, let us choose parameters at which the cross-attraction is slightly stronger than the self-repulsion. Then eventually, after rescaling, we will have the sign minus, which corresponds effectively to the self-attraction. And then if this balance, compensation between the internal self-repulsion and cross-attraction they are almost exactly balanced, and only slightly the cross-attraction is stronger, in that case, one should take into regard also this Li Huang-Yang correction in each component, because normally it's very small. But when we have the almost exact compensation between the usual mean field terms, this additional term may become important. And this term, it seems a little bit strange. It's non-analytical because it contains the third power of the absolute value, not an even power. Nevertheless, this is the form of the Li Huang-Yang correction with some positive gamma. Positive means it is always a self-repulsive component. And now we have the following effective equation. Somewhat similar to this elementary topic which we discussed last week, namely the competition between the cubic self-attraction and quintic self-repulsion. Now we have the competition between the specially organized cubic self-attraction and quartic, not quintic, but quartic, fourth order self-repulsion induced by the effect of Li Huang-Yang. And now this equation has a good chance. First of all, it's obvious that it will definitely suppress the collapse because the leading high-order term is self-repulsive. So it will definitely stabilize the fundamental modes without vorticity against the collapse. And therefore, one should be able to predict such soliton-like self-trapped states. And following Petrov, actually, they usually are not called solitons. They are called quantum droplets. Why quantum droplets? Because they are like droplets of the superfluid produced by this model, but essentially they may be considered as soliton-like objects. Yes.
The Li Huang-Yang, they consider the volume of model around the mean.
Yes.
And is it correct to understand the origin of this quantic self-repulsion from the Bogolyubov?
Yes, this is how it was derived. Yes.
So this is effective theory.
Yes, yes, effective correction, of course. Yeah, so this is, according to all this the analysis developed very long ago by Li Huang and Yang, and then adjusted for the Gross-Petaevsky equation by Petrov. This is how you can correct the Gross-Petaevsky equations if the mean field nonlinearity is made very weak, according to this trick, then it's necessary to take into regard this additional term. Okay, so then one can, first of all, look for stationary solutions to this equation in this obvious form. So this is the equation for the stationary wave function phi, which may be real in the case when we have no vorticity. And then there is a simple prediction because of the competition between cubic self-focus, self-attraction, and quartic self-repulsion. The density of state in this localized object can never be a square of the density. Square of the density. So this is the square of the wave function, exactly the density. The density cannot exceed this particular maximum value. This means that if you want to put many atoms into this object, you cannot make its amplitude large. You can only make it very broad. Therefore, one can say that because the density cannot exceed a particular maximum, one can say that effectively the matter which forms this object is incompressible. Its density cannot exceed a particular value, and therefore it's interpreted as an ultra-dilute quantum fluid. Actually, people say that this is the most dilute quantum fluid which is known in nature. Its density is smaller than the density of atoms in liquid helium, for example, in the famous quantum fluid by something like, I don't remember exactly, 5 or 6 orders of magnitude. Okay, so these are examples of such solitons. As I said, if the number of total normal number of atoms is not too large, we will have such a soliton-like object. If you want to put a large norm, as I said, we cannot exceed this maximum value or top value of the density. Therefore, we can only make this object very broad, so to say, very fat. And then it becomes, it seems like indeed a droplet of a superfluid. Therefore, it's called a quantum droplet. Okay, then what is very surprising, very soon after this theoretical prediction of Petrov, essentially 3 years later, these quantum droplets were demonstrated experimentally. So the very first demonstration was reported by the group of Leticia Teruel from ICFO. This is a famous institute in Barcelona. And she worked, her group worked with binary condensate, which is a mixture of 2 particular atomic states of potassium-39. And so this is a result from the observation from the experimental work. When the strength of this attraction between 2 components was too small, too weak, they would create this initially some localized object, but it will immediately start to decay, spread out. When the strength was too large, then they observed collapse. Then this disaster happens. However, when they selected the appropriate value by means of, once again, of the Feshbach resonance, they selected the appropriate value of the mean field attraction, they could observe this effectively stable, localized, self-supporting state, and this is a quantum droplet. Actually, this quantum droplet is not truly 3-dimensional. It's not truly 3-dimensional, it's quasi 2-dimensional, because this experiment was performed in such a way that in one direction, the localization was not intrinsic, it was imposed by the external traffic potential because of some peculiarities of this experiment. However, in another experimental work, it was possible to create a fully isotropic 3-dimensional quantum droplet using the same atomic species, the same mixture of 2 atomic states in potassium. This was an experiment performed by the group of Professor Massimo Inguscio in Florence. And this is another famous image from their work. So first, this is the illustration of what happens when the attraction between 2 components is not strong enough. everything trivially decays, but when they selected the correct value, they could observe this effectively stable object. And now this is indeed the image of the three-dimensional object. So this is fully isotropic three-dimensional object, practically unaffected by the presence of the trapping potential. Okay. Then the next question is, okay, if it is immediately obvious theoretically, and it was demonstrated experimentally, that one can create stable quantum droplets without any vorticity, without any topological structure, why not to try to embed vorticity and make them topological objects? Thus far, this issue was considered only theoretically. First of all, in the two-dimensional limit, it was done in this work, essentially performed by the group of Professor Yongyao Lee at the Foshan University. And here are some results. So it was found that indeed this model admits a large number of stable solitons with embedded vorticity. In particular, these are top views of the density distribution in such two-dimensional vortex droplets. So here is what with a small internal inner hole. This is vorticity 1, therefore the inner hole is small. Then this is vorticity 2, vorticity 3, vorticity 4. They all are shown for the same total norm of this droplet, and the result of the analysis, as these are actually cross sections of the same objects, and the result is essentially these three droplets with vorticity 1, 2, and 3 are stable. The last one with vorticity 4 is unstable, and then this is a summary of the results. So if they're unstable, they split spontaneously into fragments, something which we already discussed. Now, if this is a summary of results. First of all, if we try, S is the vorticity, it takes integer values. If we try to take larger and larger vorticities, first of all, for the existence of such droplets with embedded vorticity, it's necessary that their norm is shown here, must exceed some minimum value shown by the red curve. However, if we immediately above this curve, we will create unstable vortex droplets, and if we want to make them stable, we must make the norm essentially larger, so that, for example, as you can see here, we should have a situation when we have a really large droplet with a small inner, relatively small inner hole. In that case, it has a chance to be stable. And so for the stability, it's necessary to have the norm which exceeds this particular critical value, which is shown by the green curve. And so this explicitly stable vertical droplets were found up to vorticity 5. Probably they exist even for larger values, but just this was not explicitly considered. And now, finally, this analysis can be performed for the full three-dimensional model, because these results were two-dimensional. For the full three-dimensional model, it was done in another work, and this is the result. In principle, if we take again this three-dimensional droplet with embedded vorticities, therefore we have the hole, so it seems like a donut or torus. It is unstable against spontaneous splitting, the well-known picture. However, if we take the norm large enough, again, for the stabilization, we should take the norm which is large enough, which means the size of this object becomes large enough, which means it's more difficult to simulate it simply because it's necessary to have a very large simulation domain. But anyway, one can indeed find the values of parameters at which this three-dimensional droplet with embedded vorticity 1 with a relatively small inner hole is stable. It's illustrated here. So this is the result for vorticity 1, and explicitly also was found the stability region for vorticity 2. High values were not considered because then the integration domain should be extremely large. Okay, so this is some relatively recent review paper on the topic of these quantum droplets. Okay, and then actually here already I can arrive at conclusions. However, I will have something to add. Okay, the conclusions are, first of all, so to say, to this part of this talk, that we have this well-known problem of the propensity of multidimensional solitons, on the contrary to the behavior of their one-dimensional counterparts. They tend to be unstable in the natural models such as the nonlinear Schrodinger equation with the cubic self-attraction, and they are unstable because of the possibility of the critical collapse in 2 dimensions and supercritical collapse in 3 dimensions. And then various possibilities were developed chiefly theoretically to stabilize such solitons. Especially challenging is the objective to stabilize solitons with embedded vorticity against all these instability mechanisms. So one of the mechanisms is very straightforward. One should take the competing self-focusing and self-defocusing nonlinearity, or a more sophisticated possibility is that one can take just the system of 2 equations with the cubic self-attraction and apply the purely linear effect in the form of the spin-orbit coupling, and it's possible to stabilize and produce completely stable solitons which realize the otherwise missing ground state in this 2-dimensional system. Okay, so on top of all this, there are some additional, more sophisticated results, and maybe it makes sense to spend about 10 minutes remaining to discuss them, because I guess they may be of more specific interest for some participants of this conference. Okay, so it should be said that, of course, the general remark is that, as well as many other cases, here the theory is advanced much farther than the experiment. Nevertheless, rather surprisingly, at least one particular scenario for the experimental stabilization of soliton-like objects was implemented. These are quantum droplets, which I mentioned, where the stabilization is provided essentially by the competition between the cubic self-attraction and quartic self-repulsion. Quartic self-repulsion, in that case, is a fundamental effect which is provided by the Li Huang-Yang corrections to the mean field. And it was demonstrated experimentally that it indeed provides stable soliton-like objects without vorticity, and also theoretically it was predicted that they may be stable in the presence of the vorticity. Now, as concerns the development, as concerns the development of the experiment, obviously it will be very relevant to demonstrate experimentally such theoretically predicted stable solitons, especially vortex solitons in other cases. Thus far, as far as I know, no one has even tried to create a stable quantum droplet with embedded vorticity. So I asked the experimentalists, they said, for some reasons, it seems quite difficult for them. Okay, so as a matter of fact, they didn't try. As concerns the development of the theory, it may be also quite interesting to try to produce models and solutions of these models with a more sophisticated topological structure, such as skyrmions and Hopfions, which already were discussed in several talks here. And in particular, if we want to talk about this, oh, I should switch it here. Okay. In particular, one relatively simple possibility, which was, of course, elaborated thus far only theoretically, is to use a model which seemingly is extremely simple. It's written here. So this model is just a single nonlinear Schrodinger equation, nothing else, for the single component of the complex wave function psi. It's written in 3 dimensions, maybe also written in 2 dimensions. Now, what is sort of new in this model is the fact that the coefficient in front of the cubic term, first of all, is positive. Positive, let me remind, it means that it amounts for the self-attractive interaction. So this means that, for example, if we want to implement it in terms of Bose-Einstein condensates, this is the most natural situation. Because normally this nonlinearity of matter waves is always self-repulsive, simply because when atoms collide, they just bounce back, unless you apply special tricks such as the Feshbach resonance. Okay, but now what is assumed here is assumed that, again, actually using the control mechanisms, such as, for example, the Feshbach resonance, because one can apply this magnetic field which controls the Feshbach resonance, so that the field itself is spatially inhomogeneous, non-uniform. And then one can assume the situation when, due to the action of this external spatially non-uniform control mechanism, the size of this coefficient depends on the location. And now it's necessary to assume that it has a minimum at the center r equal to 0, and then sufficiently steeply grows from the center to periphery, from r equal to 0 towards r going to infinity. Actually, there is a very simple prediction, the analytical prediction. This coefficient, in the three-dimensional case, this g should grow faster than r to the power 3. Why? Because what we want to do, we want to predict in this, so the idea is to predict a soliton in the case of the purely repulsive nonlinearity. How we can do it? How can the object be made self-trapped in spite of the fact that the nonlinearity is completely self-repulsive? The idea is at the center, self-repulsion is weak, but far from the center is very strong. Therefore, although these atoms always repel each other, they will prefer to minimize their energy, living together close to the center where they have the smallest increase in the energy due to this mutual repulsion. And then the necessary condition, of course, is that if we want to predict such a localized state, we must demand that its norm it converges, the state is normalizable. And the condition of the normalizability of the wave function predicted by this model amounts to this simple condition. If you have dimension d, g must grow at infinity faster than r to the power, which is equal to the dimension d. Actually, now I will show some results which we obtained for a much steeper modulation profile, anti-Gaussian, like so it grows as an anti-Gaussian, like so very steeply. In principle, the results can be obtained just if you take, for example, r to the power 4 or 5, but numerical results, it's much easier to obtain well-defined numerical results for this very steep scenario of the modulation. And now let us look at what happens in this case. So in this case, we can look for stationary solutions in the usual form, as a matter of fact, which means it's written in the cylindrical coordinates r, theta, and z, and then m is an integer, which is nothing else but vorticity. So we can look for self-trapped solutions with embedded vorticity. Mu is, again, as before, the chemical potential. And now we can obtain many different solutions. For example, we can obtain, first of all, fundamental solitons without any vorticity. Then we can obtain vortex solitons with embedded integer vorticity m, but also it's possible to predict Hopfions. So Hopfion will be essentially a vortex torus, a vortex ring, however, with additional feature. This torus, it is additionally twisted, and its twist is characterized by its own topological number, which we call S. So we have two topological numbers. Simply M is the usual overall vorticity, plus S is the intrinsic twist of this inner core or pre-image, if you want, of this object. So this is an illustration, the distribution of the density in such an object. So here, this is a Hopfion when the vorticity is equal to 0, but nevertheless, this object exists without vorticity because this intrinsic twist is 1, S. Here, in all these three cases, the intrinsic twist is 1. Here, vorticity is 0, vorticity 1. Therefore, we have this central axis, and vorticity 2, where the central axis is thicker. And these are cross sections, which shows the distribution of the density. And these cross sections, they show the distribution of the phase to demonstrate that here we have 0 vorticity, here vorticity 1, here vorticity 2. And these are also cross sections, but in the top view, to show the distribution of the density in these objects. So because they may be interpreted as Hopfions, because these are objects which have the same set of two independent topological numbers, S and M in our notation, which characterize Hopfions. And what is interesting here, usually in most cases, when people try to construct sophisticated topological objects such as skyrmions or hopions, it's known that if you want to construct skyrmions, the minimum demand is that you must have a system of two complex wave fields, two wave functions. Here, quite surprisingly, it's enough to have a single wave function with the spatial modulation of the nonlinearity, and it makes it possible to introduce the hopion, and as I will show now, it has some sufficiently well-defined stability region. Okay, so this is the result of the stability analysis, the Rex simulations, and what happens is that depending on the parameters, this hopion may be quite stable. First of all, when its vorticity is equal to 0, and we only have s equal to 1, the intrinsic twist. Now, if we take the cases when both vorticity and intrinsic twist are both equal to 1, then there are two different parameter regions. In one, it is unstable, but in another region, which has a sufficiently large size, it is stable. Finally, if we take any value of vorticity larger than 1, or any value of s larger than 1, they are always unstable. Now, actually, when I showed this formula, actually this formula is an ansatz for which reproduces, somehow reproduces, tries to reproduce the hopion. It's the simplest ansatz. So if you look at this factor, it's easy to understand that indeed it tries to reproduce this intrinsic in terms of the cylindrical coordinates with integer s, which s should be positive, of course. It tries to emulate this intrinsic twist. And as concerns the vorticity was already introduced here when we defined this function w in terms of the full wave function psi. Okay, so it's not simply an illustration. It can be used for some analytical calculation. Namely, we can write the Lagrangian of the system of the stationary equation, substitute the ansatz, and try to apply analytically the variation approximation. And in spite of the fact that obviously we are trying to approximate a very complex object, this variational approximations, quite surprisingly, it's analytical and it produces rather accurate results. And now an illustration of this fact, of this finding, is here. So this is a summary of results. It shows actually the capital R is the radius of the center of this pre-image of the central core of the hopion, for example, this central core. So it has this radius, obviously. So we can try to collect the results and show is R is a function of the total norm. So this is a dependence for different values. So in all the cases, intrinsic twist is fixed to be 1, and we have 3 different values of the external vorticity: 2, 1, and 0. So the red curve shows that it's unstable. So for m equal to 2, it's completely unstable. Here, the red portion is unstable for m equal to 1, but here it is stable. The black one is stable. As I mentioned, there are stable hopions when both m and s are equal to 1. And finally, this is the branch of hopions when we have 0 vorticity, only the intrinsic twist is present. It's completely stable, and actually this one is quite accurately predicted analytically by the variation approximation. It's shown, this prediction is shown by the chain of the green points. Okay, and now one more dynamical effect for this hopion. We take the simplest possibility hopion with zero vorticity, only with intrinsic twist. We know it's completely stable. Now what we can demonstrate the existence of another dynamical regime of motion for it. We can apply the torque to it, and under the action of the initial torque, this ring starts to demonstrate persistent rotations about its axis. About this axis, it starts to rotate. And this seems to be a completely persistent regime of dynamics. Okay. Now we can take exactly the same model. At this time, we can take not the hopion, but just a soliton with a topological charge. And then we can demonstrate another dynamical regime. Actually, this vortex soliton demonstrates the behavior of a gyroscope. So this is a stable vortex soliton with embedded vorticity 1. Then suddenly we apply in the perpendicular direction a torque. This torque actually aims to initiate the precession of this gyroscope. So this set of lines shows the collection of orientations of the central axis of this vortex soliton in the process of its precession. So it performs the precession, roughly speaking, along this conical surface. So this is again a stable regime. This vortex solitonic gyroscope can be quite stable. And then one more, if exotic thing, we can take not exactly the same model. We can take the model in which this spatial modulation is stretched in one direction in the so that we give it the shape of shape of such a nut and peanuts. Sorry, shape of a peanut. Some people forgot the word peanut. And then another exotic regime which can be obtained is the so-called hybrid vortex. Hybrid vortex means the following: when we have this peanut-shaped modulation, it's possible to construct a solution which consists of two, one vortex here in the top part, another vortex in the bottom part, and we can create them with the opposite vorticities, as is shown here. It is a +1 and -1, or +2 and -2. Then it exists as a stationary solution. Of course, when we combine opposite vorticities, we break the axial symmetry. This object is not axially symmetric. And in case when both vorticities is + and -1, it also may be stable. And actually, this can be easily checked by the direct simulations. And now the very last remark concerning a different type of the dynamics, but maybe also interesting. Actually, today, for example, Professor Chiwen John mentioned a well-known topic, which recently became rather fashionable, the study of spatio-temporal vortices. So what I just wanted to mention is the fact that relatively long ago, in 2010, we had this paper with my former student. And in this paper, actually, as far as I know, it was the first one in which the concept of spatio-temporal vortex solitons was explicitly introduced. So at that time, we did not know that the topic would be so fashionable. Therefore, the spatio-temporal vortices are not mentioned in the title, but they are explicitly mentioned in the abstract and later, of course, in the text of this paper. So these spatio-temporal objects, they were actually two-dimensional. So we can see that in terms of optics. Actually, one can say that this dimension was not 2, but in a sense 2.5. Why 2.5? It was a dual coplanar waveguide. So we had a spatio-temporal two-dimensional soliton, but with two components and two parallel waveguides into parallel cores. And then we explicitly found for the spatio-temporal soliton stable regimes when it carried explicitly the spatio-temporal vorticity. And as I said in that early paper, it was explicitly called by exactly the same name, which became quite popular more recently, spatio-temporal vortices. And the difference from, for example, what Professor Chiwen John told today is that he told about linear spatio-temporal vortices. We talked about this spatio-temporal vortex, which is a soliton, is a self-trapped, self-supporting object in the nonlinear system. Okay, this is, I think, all, and thank you very much for your interest.